last two modules where we were looking at the energy equation, I will give you a very brief recap. We started with the energy equation, this one, used order of magnitude analysis and simplified this to this form which we can use. We took viscous dissipation into account and kept this term, and we also said TW is a function of x, a very general case. We defined quantities this way for theta, and T wall minus T infinity was equal to Gx, which is a function of x. T infinity was taken as a constant. The similarity variable was exactly as what we defined before. After having done that, we wrote the expressions for t dt by dx, dt by dy and all these things in terms of the new variables. Then substituted for these things in the energy equation and got expressions which looked like this. Okay, substituted for u and v from where we had in the momentum equation, wrote d theta by dx and d theta by dy in terms of d theta by d eta and d eta by dx. Okay, so my energy equation had u d theta by dx look this way, v d theta by dy look this way, and then we had an extra term u theta by g dg by dx. This was for because wall temperature was varying. This was not going to 0. Right hand side was this, and then we manipulated the viscous dissipation terms by substituting for u as u infinity f prime, and then doing the maths, we got this as 2 into local Eckert number by x f double prime squared times u infinity. Next, we put everything together. In doing so, first term was u d theta by dx, second term and the third term was v d theta by dy. Okay, v d theta by dy. We had expanded the bracket. This extra term in black was the term which was there because of the wall temperature not being equal to constant. This one just remains as it is. We just copied it. We had forgotten in a couple of steps. We went back and copied it. Right hand side was these two terms which we had seen. We do expansion of this bracket, and then we see that the first term cancels with the second term on manipulation. We have this term from v d theta by dy and this term from the varying wall temperature remain. Right hand side remains this way. So we went on to manipulate this a little bit by calling nu over alpha as Prandtl number by definition, multiplying by x, so on and so forth, and we cancelled off u infinity. So my energy equation comes to a form which looks like this, Then we have terms like x over n dn by dx. So we went on to manipulate that. This by definition of n, which is u infinity mu x whole to the power half, we substituted for u infinity is cx to the power m, and then when we went on to define this, we came up with the fact that x over n dn by dx is equal to m plus 1 by 2, where m is the pressure gradient parameter. Remember from the momentum equation, m is the pressure gradient parameter, m equal to 0 for flow over a flat plate. So substituted this here. So this term was a part of here, this term, substituted for this, regrouped the terms, and we got this differential equation. And we went on to argue that this differential equation, of course there are two boundary conditions. This is a second order ODE. So I'll write the boundary conditions later. So for this to have similarity solution, this quantity and this quantity should only be constants. We should not have any x dependency in the final form. Therefore, we said x by g dg by dx and Eckert number both should remain constant. We call this as gamma, and we wrote g of x is this way. So let us consider x by g dg by dx is equal to gamma. We did the mathematical manipulation of separating the variables, and we said g is equal to delta t reference x to the power gamma. We looked at Eckert number. This is half u infinity squared, which is half of cx to the power m squared, which is c squared x to the power 2m, cp delta t x gamma comes for this. When we simplified, we came up with this form. And this, for this to be a constant, c is a constant, cp is a constant, delta t reference is a constant. This also has to be a constant, which means x should be equal, gamma should be equal to 2m, which means when viscous, now we will start from here. So for similarity to exist, when viscous dissipation not equal to 0, then gamma can take the value 2m only, because we have to satisfy both these and they are not mutually exclusive. So once I pick m, your hydrodynamics gave me m, right? M is pressure gradient parameter, remember? And then m equal to 0, m is equal to 0, flat plate, m is equal to 1, stagnation point flow, and then it said m less than minus 0.2, non-physical because separation occurs. So we have a few restrictive cases of m, but if we want to have viscous dissipation effect to be quantified, gamma can take the value 2m only. If viscous dissipation is equal to 0 or we neglect it, we neglect viscous dissipation, that means you're talking of low speed flows where this is neglected. From this we can say that gamma can take any arbitrary values. Gamma can take any values. And again, I went on to say this, we are not saying that u infinity is a constant or t wall is a constant. We are not saying that. We are saying this ratio which has a complex dependency on u infinity and tw, like here u infinity squared twx minus t infinity, whatever be the functional form, this should be constant. Again here this quantity should be constant. Okay, so based on this we said viscous dissipation being present, your gamma should be equal to 2m. When viscous dissipation is neglected, gamma can take any value for similarity to exist. Okay, now let us keep in mind, just let us go back here, dp by dx is equal to minus rho u infinity du infinity by dx. Therefore, this is going to be, if you substitute for u infinity c x to the power m, this will come out to be minus m rho c squared x to the power 2m minus 1. dp by dx is strongly dependent on m, which is the pressure gradient parameter. So my differential equation ODE now looks like this. I am just rewriting what was written in slide number 9. Theta double prime plus Prandtl number m plus 1 by 2, just making it look a little nicer, f theta prime minus f prime, and I am going to write the definition of gamma here. xg by g dg by dx we chose as gamma. We chose this as gamma. So I will just write this as gamma into theta. Gamma into theta plus 2 times Eckert number local f double prime whole squared equal to 0, where gamma is equal to x by g dg by dx. Okay, this is my ODE. What are my boundary conditions? What kind of an equation is this? Second order ordinary differential equation in eta as the independent variable. So what are my boundary conditions? At eta is equal to 0 or y equal to 0, t is equal to t wall, which means theta of eta equal to 0 is 1. What is my definition of theta? T minus t infinity divided by t wall minus t infinity. Second, as eta tends to infinity, t tends to t infinity, theta as eta tends to infinity is 0. So these are my boundary conditions. Two boundary conditions, second order ODE. So technically I should be able to solve. What does this mean? My theta, when I solve, theta therefore as a result is going to be a function of, what is it going to be a function of? Type of the fluid, of course, so Prandtl number would be there. Gamma, what we choose, so M, pressure gradient parameter. Gamma, what we choose, local Eckert number, Prandtl number, and also the suction or blowing parameter. What is that? Suction or blowing parameter was where you took care of the VW. VW was the thing which took care of the fact that you had either suction or blowing. So this we call as the blowing parameter. This is suction or blowing. I did not define this explicitly. This is basically a collection of terms involving VW. Suction or blowing parameter, which is nothing but having VW dependency. Suction or blowing parameter is group of terms with VW, is VW dependency. So, and of course your eta, which is your independent variable. So when Eckert number equal to 0, you lose out on this, you just have five dependent quantities. When Eckert number is equal to 0, you just have 5 quantities. When Eckert number is not equal to 0, you have 6 quantities which dictate the solution. So this is a functional requirement of my solution. So now let us quickly go through the solutions. We define enthalpy thickness. Enthalpy thickness, just as momentum or integral thickness, this is 0 to infinity rho Cp u t minus t infinity divided by rho Cp u infinity. These are all infinity level properties. T wall minus t infinity dy. This, when you cancel off the property terms, you will get 0 to infinity u by u infinity t minus t infinity divided by t wall minus t infinity dy, which can be written as 0 to infinity theta of eta f prime of eta dy, and y is equal to, remember, eta is equal to y under root u infinity by nu x. Therefore y is equal to nu x over u infinity eta, dy is equal to nu x over u infinity d eta. Correct? This is, if I multiply and divide by x, this I would get as dy is equal to nu over u infinity x times x d eta. Correct? So this is going to be dy is equal to x d eta by Rex. Therefore, this will be substituted here. I would get delta 2 or enthalpy thickness is 0 to infinity theta of eta f prime of eta x d eta by local Reynolds number square root. Therefore, if I move these things to the other side, non-dimensionalization of the enthalpy thickness. So x would be taken delta 2 over x square root of Rex is nothing but 0 to infinity f prime theta d eta. Okay, and what is this quantity? We are going to just see in a minute. So this, let us keep it aside. We are going to consider h of x, local heat transfer coefficient, which is wall heat flux divided by local wall temperature minus T infinity, which is minus k dt by dy at y equal to 0 T wall minus T infinity. this is function of x, of course, t wall minus t infinity. Theta is equal to t minus t infinity divided by t wall minus t infinity. Therefore, I get, substitute for this, I would get this as hx is equal to minus k d theta by dy at y equal to 0. So, this tw minus t infinity theta, differentiate with respect to y, this is constant, you get this quantity. So, once I get this, I will write this as hx is equal to minus k d theta by d eta at eta equal to 0 d eta by dy, d eta by dy, which is equal to minus k theta prime of 0 under root u infinity by nu x. From the earlier definition, this was my definition of d eta by dy. Therefore, I would get hx is equal to, so let us bring this, hx into x by k is equal to minus k theta prime of 0 divided by k, I am multiplying and dividing by x by k, u infinity x over nu x, like this, x divided by k. So, k will cancel, this is going to be equal to minus theta prime of 0 u infinity x over nu to the power half, and what is this? What is this quantity? Reynolds number. Therefore, hx by k is local Nusselt number is equal to under root local Reynolds number times theta prime of 0. There is a minus sign, which means if I regroup this, nux divided by root of rex is equal to minus theta prime of 0. Very useful result. What this means is the gradient theta prime of 0 is nothing but a direct measure of Reynolds number. Now, you go back and look at our results. F prime of eta was u by u infinity. F double prime of eta is du by dy, wall shear stress, because this was defined this way, correct? Wall shear stress. Theta is t minus t infinity by t wall minus t infinity. Theta prime of eta is nothing but Nusselt number. So, because the derivative was defined as velocity, f prime was the velocity, we got there f double prime. F double prime was obtained for Cfx. Cfx was obtained this way, na? The function of f double prime something something, Reynolds number dependency. Here you have theta prime. So, it follows the logic very beautifully, and now we define Stanton number. Stanton number is defined as hx by rho u infinity Cp RePr, which will come out to be Nusselt local by Re local Pr. Therefore, what we are trying to say is we got here nu by Rex. This is nothing but minus theta prime, or Stanton number is also a function of the fluid and the gradient of the temperature. So, what is different from hydrodynamics here is the momentum diffusivity ratio with the momentum diffusivity and the heat diffusivity, which comes under Prandtl number. So, type of the fluid is going to be directly taken care of by this theta prime of 0. So, when I do experiment for different fluids, it would turn out that nu by Rex would have different gradients, and that different gradients would be directly related to the Prandtl number. So, local quantity Nusselt number we have defined. Now, let us consider now for flat plate. We are going to the final case here. Flat plate m is equal to 0, therefore, T and T wall is equal to constant. Therefore, gamma equal to 0, viscous dissipation is 0, which means Eckert number equal to 0. What does my governing equation become? My governing equation, when gamma is 0, Eckert number is 0, flat plate m is equal to 0, I get theta double prime plus half f theta prime equal to 0, or Prandtl number by 2, sorry, PR by 2 f theta prime equal to 0. What was my momentum equation? F triple prime plus 1 half f double prime equal to 0. What were my boundary conditions here? Theta at 0 is equal to 1, theta at infinity equal to 0. What were my boundary conditions here? F prime of 0 is equal to 0, f prime of infinity equal to 1, f of 0 equal to 0. This was my V condition. Now please take a moment, step back and look at this. Just look at these two equations and the boundary conditions. If Prandtl number was equal to 1, aren't these functional forms identical? Aren't these identical? How? Look at this. F prime was my velocity. We had to define that way. Theta was my temperature. So second derivative of temperature, second derivative of velocity. It comes out as f triple prime because u was f prime. F as it is. Theta prime is first derivative of temperature. F double prime first derivative of velocity. Right? Theta temperature, f prime velocity. Wall condition, no slip, no slip. Infinity condition, t equal to t infinity. Infinity condition, u is equal to u infinity. The way we have defined makes this 0 and 1 opposite. So what we are trying to say, if Prandtl number is approximately equal to 1, if Prandtl number is equal to 1 and we define theta prime or theta is equal to 1 minus f prime, if theta equal to 1 minus f prime, that means the solution of this, second derivative of this, you substitute here theta of 0, f prime of 0. F prime of 0 is 1, theta of 0 will be 0. Okay, so theta, let us just substitute. So theta of 0 is equal to 1 minus f prime of 0. F prime of 0 is 0, therefore theta of 0 is equal to 1. We got this. Similarly, you put theta of infinity is equal to 1 minus f prime of infinity. F prime of infinity was 1, therefore theta of infinity is equal to 0. We got this. So if I define my solution for theta this way, and if Prandtl number equal to 1, the non-dimensional, I am not saying, please note this very carefully, non-dimensional form governing equation and non-dimensional boundary condition are identical. If that be the case, can we say the for Prandtl number approximately equal to 1? If that be the case, can we say that the non-dimensional solutions are identical? If this is satisfied, this means non-dimensional solutions, because non-dimensional governing equation and non-dimensional boundary conditions are the same, this non-dimensional solutions are identical. This is what is very, very powerful tool, and this is called as the Reynolds analogy. Okay, so we just go to some basic results. We say now, remember our scaling analysis gave me what? Nu is of the order of Re to the power n, Pr to the power n, and we got this as half and 1/3, half and half depending on the situation. So if I say the solution of this ODE, Prandtl number, if I put for air, which is 0.71, if I put for water, this is 5 and say so 10, minus theta prime of 0, when I solve this equation in coupling with the, solve the energy equation in conjunction with the momentum equation, this would come out to be 0.291, 0.33, and these would be 0.572 0.721, so on and so forth. So when Prandtl number equal to 1, remember we got that f double prime was 0.33. This is the same. Okay, so we are going to see when I plot these things together, I would get, when I group these results, I would get Nusselt number is equal to 0.332 Re to the power half PR to the power 1/3. Similarity method had given me this functional form, and now this minus theta prime of 0, this order of magnitude was replaced by an equal to sign by putting in a constant, and that constant was 0.33. This is where you get your correlations from. These are not black magic. You need to tell your students, please don't by heart the correlations. Unfortunately, a great deal of importance is given to by hearting the correlations. So we are not here to by heart correlations. These are available. You need to tell them where these came from. When we do integral method solutions, we would get a slightly different coefficient because of the approximation involved, but the functional form is the same. And if this is done for high Prandtl number and low Prandtl number cases, we are just going to complete this part. Low Prandtl number and high Prandtl number cases, the solution of this differential equation for low Prandtl number and high Prandtl number cases, scaling gave me Nu is of the order Re to the power half PR to the power half. Scaling gave me Nu is of the order Re to the power half PR to the power 1/3. This solution, this kind of solution, similarity solution, is going to give me Nu is equal to 0.564 Re to the power half PR to the power half. This is going to give me Nu equal to, this order gets replaced by an equal to sign, 0.339 Re to the power half PR to the power 1/3. And believe it or not, these are what you would see in textbooks as correlations for very high Prandtl number greater than 1, correlations for Prandtl number less than 1. And scaling analysis gave me this powers. What I got as coefficients, which is minus theta prime of 0, was by putting this, running this solution using some Runge-Kutta algorithm or something like that in conjunction with the momentum equation. So with this, we come to the end of the scaling analysis, where we come to the end of the similarity method. We saw in scaling the functional form of the Nusselt number. We got the coefficients for Nusselt number here, and these coefficients are what is seen in your correlations, laminar flow correlations. Next, in integral method, we will use an approximate profile, and we would get similar expressions for boundary layer thickness delta, for coefficient of friction, and also for Nusselt numbers. Those coefficients will be slightly different from what we got here because this is an exact solution. Mind you, similarity method is very restrictive because of the several constraints we had to impose. Gamma equal to 2m when Eckert number was considered. So we had several restrictive cases. We couldn't go for any arbitrary case in case of similarity analysis, whereas integral method allows you a wide variation of profiles, but the solutions will be more and more approximate if you take approximate profiles. Thank you.